Hello everyone, I am Malina Bedira from MIT and I'll be presenting our work on Chronos, efficient speculative parallelism for accelerators. This talk is based on a paper at ASPLOS 2020 and this is joint work with my advisor, Professor Daniel Sanchez. We observe that current accelerators have mostly focused on applications with easy parallelism, where tasks and dependencies are known in advance and parallelism is easy to extract. These kind of problems are common in domains like deep learning and genomics. In contrast, Chronos targets applications which are hard to parallelize, where speculative execution is often required to extract parallelism. These kind of applications are present in graph analytics, simulation, and transactional databases. In order to build Chronos, we had to overcome one significant challenge. Prior speculation mechanisms, such as transactional memory, require a global conflict detection mechanism. This is because these systems allow any transaction to run on any core and access any region of memory. Upon a conflict, the entire system needs to be checked for conflicting tasks. In prior shared memory systems, such global conflict detection is implemented by extending the cache coherence protocol. However, accelerators usually do not have coherence protocols, and implementing one would add overheads. Hence, we rely on a different conflict detection mechanism. We limit the data that each core can access and divide each transaction into tiny tasks, which are then sent near to the data they operate on. To maintain the atomicity of the original transactions, these tiny tasks are sequenced through order constraints. Under this scheme, all conflicts become local and no coherence is needed. Using this insight, we propose two contributions. Slot, or spatially located ordered tasks, is a new execution model that does not require coherence, but instead rely on task mapping and task ordering to detect conflicts. Chronos is an implementation of Slot that provides a common framework for acceleration of applications with speculative parallelism. We use Chronos to build accelerators for several hard-to-parallelize applications, achieving significant speedups for a 40-threaded baseline CPU. Chronos is open source and can be accessed from this URL. To illustrate speculative parallelism, we look at DES, a discrete event simulator for digital circuits. DES computes the waveform of each wire by tracking when the logic state of a wire toggles. For instance, the OR gate here starts with both inputs at 0 and the output also at 0. If one of the inputs was changed to 1 after some time, the output of the gate also toggles, which propagates downstream to the XOR gate after a certain delay. Here, we assume gates take no time and all delays are pushed down to the wires. We represent a simulation of this circuit by a task diagram, where the toggling of each input to a gate is a separate task. In this diagram, x-axis represents time and y-axis represents the gate a task operates on. In the beginning, task O1, which represents the toggle of one input to the OR gate, creates a new task x6 when executed. However, x6 is not safe to be executed non-speculatively because another task could operate on the XOR gate before time 6. To illustrate such a scenario, let's assume that one of the inputs to the NAND gate changes at 2 nanoseconds. This causes a new task at x3. At this point, if speculative execution of x6 has already begun, x3 should abort task x6 and re-execute it. Prior systems that performed such speculative execution required global conflict detection. This is because they allowed any task to run at any core. Let's assume a situation where O1 is run at core 1, x6 at core 2, N2 also at core 2, and finally x3 is starting to run at core 1. Now x3 needs to find and abort all tasks which access the same gate but at a higher time. It does so by sending messages throughout the memory system, relying on the coherence protocol to find other tasks which access the same data. In contrast, we remove the requirement for global conflict detection by mapping same object tasks to the same core. For example, if the OR and NAND gates are mapped to core 1 and the XOR gate is mapped to core 2, all accesses as well as conflicts will be local to a core, making the directory redundant. Now, it may seem like this scheme only works if tasks accesses a single object. Next, we will look at an example of how we can leverage order to extend this scheme to tasks that access multiple objects. Consider a banking application where transactions transfer money between accounts. Each transaction must atomically decrement the balance of one account and increment the balance of another, requiring atomic access to two different objects. We propose to manually divide the large transactions into two fine-grained tasks that access a single object each, with the first task spawning the second. To ensure original order, we give timestamps to each task. To make sure that different transactions do not interleave, each transaction is assigned a disjoint timestamp range. This technique generalizes to any arbitrary combinations of reads and writes. Such refactoring of an application to use multiple fine-grained tasks also brings in other benefits. First, instead of bringing data to compute, as is the case in conventional systems, this scheme sends compute to the data, increasing data locality. Second, this scheme reduces network traffic because the size of each task is much smaller than the cache lines that needs to get moved around. Third, this scheme also increases parallelism, since multiple smaller tasks can now be run in parallel speculatively. Fourth, the probability and impact of aborts under this scheme, under the new scheme, is also reduced. This is because if a conflict were to be found, only the directly conflicting tiny task needs to be aborted, not the entire transaction as was the case before. Finally, in this approach, communication is asynchronous because they happen through tasks which are spawned rather than through synchronous memory accesses. Now we are ready to introduce slot, which is a programming model that enforces the condition that each task can access only a single object. Formally, slot programs consist of tasks, where each task can create children tasks through a defined interface. Creating a new task requires specifying a function pointer, a timestamp, an object ID, and 0 or more additional arguments. Here, the timestamp specifies the ordering, and the object ID specifies data dependencies, where only tasks with the same object ID are treated as data dependent. Tasks with different object IDs can only communicate through additional task arguments, since this model does not support shared memory for accesses to different object IDs. Now, tasks can be implemented either as software, functions, or specialized processing engines. Let's look at how DES could be implemented with software tasks. We first illustrate a conventional DES implementation and then show the slot code. In DES, the sync_toggle function simulates an event arriving at a gate. This function updates the gate's own state, and if the gate's output was toggled, it creates new events for downstream gates. These events are held in a priority queue, which is initialized with the initial events, and an event loop sequentially executes these events in timestamp order. In slot, the code is very similar but with two changes. First, the enqueues to the event queue are now replaced with the slot.enqueue function. Second, the priority queue and the manual event loop is now encapsulated in the slot execution model, hence requiring only a single slot.run function to invoke it. A slot implementation can choose to run these tasks sequentially or run them out of order to extract parallelism. Chronos, our implementation of slot, does the latter, where tasks are speculatively run out of order. Chronos is a framework to build accelerators for applications with speculative parallelism. Chronos implements a multi-tile system, where tiles are connected through two interconnects for task and memory traffic. Each tile consists of a private cache that is not kept coherent with those of the other tiles, and a task queue, a task unit, and processing elements to run the task logic. The application developer specifies the tasks and how they're implemented, which can either be through software routines running on soft cores or through specialized hardware processing elements. The Chronos framework takes care of task management and speculative execution. To understand how Chronos performs this speculative execution, we begin by understanding the life cycle of a task. A Chronos task is created in the idle state when a PE enqueues a new task through the slot.enqueue interface. An idle task is dispatched to run on a PE in timestamp order, and once it is finished, it stays in the finished state until it can commit. A task in any of these states can also be aborted. After the abort, the task can either be discarded or requeued. The decision to discard or requeue depends on why the task aborted in the first place. If the task was aborted because its parent has also aborted, then the task must be discarded. Otherwise, if the task aborted due to a conflict, then it is requeued back into the idle state. Now, let's look at how a Chronos tile implements this life cycle. Each Chronos tile consists of a task queue, which stores the status of all tasks, and a commit queue stores the speculative state of all running and finished tasks, similar to a reorder buffer of an out-of-order core. A PE runs the task logic, and the task send buffer buffers newly created tasks until they are acknowledged by the destination tile. We illustrate the operation of these structures through a task graph example in the DES. We assume that this is run in a two-tile system with the mapping shown on this diagram. In the beginning, we have two initial tasks, 1 and 2, which are both resident on the task queue of tile A. Now, task 1 can be dequeued and started execution in the PE of tile A. This task creates a new task with timestamp 6, which is sent through the task interconnect into the task queue of tile B. This new task can immediately be dispatched to run on B's PE. Now, let's assume that this 6 creates another task with timestamp 8 to communicate with the rest of the circuit. Assume this task is also mapped to tile B. At this point, task 1 finishes, in which case the PE writes its speculative state back onto the commit queue, and the PE is now ready to dequeue another task. Hence, tile A now dispatches task 2 to run on the PE, which would create a children task with timestamp 3. However, before task 3 can run, it must perform conflict detection with other tasks in the commit queue. Two tasks will conflict if both of them have the same object ID and one of them have a higher timestamp than the other. In this case, task 6 must be aborted to make way for task 3. Chronos aborts a task in 3 steps. First, if the task is already running on a PE, it instructs the PE to abort it. Second, if the task has created other children tasks, it creates abort messages that are sent through the task interconnect to the necessary task queue. Finally, the task 6 needs to be requeued back onto the task queue so that it can be dispatched again later for proper execution. Finally, this diagram shows all messages that flow between the components. Chronos relies on two mechanisms outlined in prior work for its versioning and commit protocols. Chronos uses eager versioning, which updates speculative values in place but stores the old values in a separate on-chip undo log. This scheme makes commit fast and allows tasks to use speculatively produced data before the producer commits. Chronos uses a GVT protocol to find which tasks can commit. In this protocol, each tile communicates the timestamp of its earliest unfinished task to a global arbiter, which responds with the global virtual time. Each Chronos tile walks its commit queue in the background and commits task with a lower timestamp than the GVT. This scheme is chosen because it achieves fast and parallel commits. Using these mechanisms, we built an FPGA implementation of Chronos which can fit up to 16 tiles and running at a frequency of 125 MHz. Since Chronos tasks are small, it is important that this implementation supports a high task throughput. On a 16-tile system, our implementation can enqueue, dequeue, execute, and commit 8 tasks per cycle. This figure shows how a 16-tile Chronos instance is mapped onto the FPGA, where different colors represent different tiles. We evaluate Chronos by building applications for 4 challenging applications and running them on the Amazon AWS FPGAs. We build accelerators for discrete event simulation, MaxFlow, single source shortest path, and A-star search. For each application, we build custom PEs. Each PE is 32-way multi-threaded, and each tile has a single PE. We compare the performance of these accelerators against highly optimized software parallel implementations running on a 40-threaded Xeon AWS instance that is similar in price to the FPGA. First, let's look at the performance of Chronos, which shows how Chronos outperforms 40-threaded Xeon baselines significantly. To understand these graphs, we need to understand that this graph is comparing FPGA and CPU. Because different FPGA systems have different number of PE centiles, these graphs shows the results as a percentage of system use. In each of these graphs, 1x is the performance of single-threaded CPU, and the red line at 100% corresponds to 40 threads. In the green line, we go from running a single concurrent task at a time to running as many tasks as can be fit on the FPGA. Compared to the CPU, the FPGA is 15.3 times faster for DES, 4.3 times for MaxFlow, 3.6 for SSSP, and 3.5 for A-star. In all these cases, the FPGA outperforms the CPU despite running at a 19 times slower frequency. So let's look at why this is faster. There are two reasons. First, this table shows that we can run a lot of tasks in parallel on the FPGA, sometimes up to 512 concurrent tasks, compared to just 40 on the CPU. Second, this column shows the performance of the FPGA with a single concurrent task compared to a single-threaded CPU variant. Normally, we'd expect a slowdown because of the 19x frequency difference, but specialization makes the gap much narrower. For DES, it's actually faster because the CPU variant uses a software priority queue, while Chronos uses a more efficient hardware priority queue. To illustrate how efficient Chronos is, this diagram shows how each PE spends its cycles, based on whether they were doing work that is ultimately committed and useful, or whether they were doing work that was ultimately aborted and wasted. Also, it shows the amount of cycles that a PE could not do any work because the commit queue was full or no task was available. This plot shows that only 11% of the cycles are actually wasted and most work is ultimately useful. In the paper, we show how Chronos performs with traditional non-speculative applications, and also how Chronos can be configured for applications that does not require rollback after task abort. We also have many more results, including how Chronos performs with RISC-V softcores, projected performance of Chronos on an ASIC implementation, and the resource utilization on the FPGAs. In conclusion, prior speculative parallel systems have relied on cache coherence to detect conflicts, precluding their use in accelerators. In this work, we propose two contributions. SLOT is a new execution model that does not require coherence but relies on task mapping and spatial task and task ordering to detect conflicts. Chronos is an implementation of SLOT that provides a common framework for acceleration of applications with speculative parallelism. We demonstrate the benefits of Chronos by using it to build FPGA accelerators for 4 challenging applications with speedups up to 15x. Chronos is available at this link, and we welcome you to check it out and provide feedback. Thank you.